It's a quiet comfort to share this moment of stillness with you. Wherever you are, allow the world outside your window to soften into shadow. Let your mind settle like fine dust in a sunbeam until all that's left is a gentle awareness of this quiet room. We're going to drift far, far away tonight, not through space, but through a thought experiment that stretches the very limits of our imagination. Imagine a kind of temperature so immense, so unimaginably high, that the very fabric of reality, time, space, and the laws of physics as we know them begins to dissolve. Tonight, we'll turn our quiet attention to the concept of absolute hot, a peak of energy where the universe is born and everything we understand breaks down into pure, radiant power. It's a journey to the highest possible note the cosmos can sing. If this gentle exploration of the universe's ultimate limit helps your thoughts slow down and your body relax, consider offering a quiet like and a soft subscribe. It helps these sleepy stories find their way to other curious minds, one peaceful soul at a time. No rush, just settle in. When you're ready, we'll step together toward the very beginning of everything. When we talk about absolute hot, we are not just asking how high a thermometer can go. We are asking about the point where heat itself pushes the universe to its limits. Temperature, at its heart, is a measure of motion. Every bit of matter you have ever touched is made of tiny particles that jiggle, bump, and spin. In a cool room, they move lazily. In a hot oven, they rush about more quickly. Inside a star, they are racing at incredible speeds, but still not quite at the speed of light. That speed, the speed of light, is a kind of cosmic speed limit. Nothing with mass can go faster than it. So as you picture turning the heat up higher and higher, it might seem like once the particles are almost at light speed, you must be close to a final ceiling. But the universe is more subtle than that. When particles draw near to that limit, their speed does not increase much more, yet the energy you pour into them keeps rising. Instead of simple motion, that energy begins to weigh on the very shape of space and the flow of time. There is a special temperature where this begins to matter in a deep way. Physicists call it the Planck temperature. It is written as about 1.4 times 10 to the power of 32 Kelvin. In Fahrenheit, that is roughly 2.55 times 10 to the power of 32 degrees Fahrenheit. The exact digits are less important than the feeling. This is not just hot. It is so far beyond ordinary heat that our normal words start to wobble. At this temperature, the particles we know are not simply moving quickly. They would carry so much energy that their gravity, tiny and invisible in daily life, would become as important as the other forces that hold matter together. The quantum rules that describe the very small and the curved geometry that describes the very large would both have to speak at once. Quantum mechanics and general relativity, usually kept in separate corners of physics, would overlap so completely that neither one on its own could tell the full story. When scientists try to push their equations into this realm, the answers stop behaving in the calm, predictable way we rely on. The math starts to hint, to stutter, to give results that do not quite line up with anything we can picture. It is as if we have walked to the edge of a detailed map and found only blank paper beyond. That blank edge is what we call absolute hot. It is not just the hottest temperature we could ever measure. It is the hottest temperature at which our current understanding of the universe still makes sense. The strange part is that this is not just a fantasy number. The universe itself seems to have passed through this state. In the briefest breath after the Big Bang, Long before even a trillionth of a second had slipped by, the temperature of the cosmos was at or above the Planck temperature. Matter, light, and the fabric of space were pressed together in a way we still cannot fully describe. It was not just that things were hot, it was that the idea of things had barely formed yet. Here, the word hot becomes almost symbolic. We are used to comparing warm and cold with our skin, our memories of seasons, our everyday experiences. In this region, those comparisons fall apart. Even the hottest objects we know become almost gentle by contrast. One of the hottest known stars, called WR102, shines with a surface temperature of about 210,000 degrees Fahrenheit. That sounds extreme, and in any normal conversation it would be. Yet against absolute hot, it is unimaginably cold, like a small candle beside an explosion that could unmake the rules of physics. The difference is not just a matter of adding more heat. It is a leap into a different regime of reality. No star can hold itself together at these temperatures. No experiment on Earth can reach them. As far as we can tell, they existed only in the first instant of the universe, and perhaps in fleeting, tiny patches that appear and vanish at scales smaller than atoms, if at all. When the mind tries to grasp this, it naturally reaches for familiar images. We think of ovens, glowing metal in a forge, lava spilling from a volcano, or the white glare of the midday Sunday. At absolute hot, those images are as distant as fireflies from galaxies. At such temperatures, atoms cannot remain whole. The protons and neutrons inside their nuclei would be torn apart into their more basic ingredients, quarks and gluons. Even those might dissolve into something more primitive that we do not yet have words for. The separate forces we meet in physics class start to blur together, as if they are different faces of a single, deeper interaction. There's an idea in particle physics called unification. It suggests that at very high energies, the forces we usually treat apart, the electromagnetic force, the weak nuclear force, and the strong nuclear force, may merge into one. Absolute hot lies near the region where this might happen. It becomes less helpful to say, this is heat, and more honest to say, this is a state where the rules themselves are melting. Temperature in our daily life feels like a simple scale, something we can nudge up and down like a thermostat on the wall. Higher means more warmth, lower means more chill. Underneath, though, temperature is really a way of talking about energy shared among particles. In a solid, they vibrate gently in place. In a liquid, they slide past one another. In a gas, they race freely in all directions. Heat is what we call the energy that feeds those motions. As more energy is poured in, the particles move faster, collide harder, and occupy more energetic states. But there is that quiet catch. Nothing can move faster than light. Once particles are very close to that speed, the extra energy cannot push them much faster. Instead, it increases their mass slightly and raises the energy density of the whole system. Because energy and mass are linked, that extra energy adds to the gravitational pull in the region, even if the region is microscopic. At the Planck temperature, the wavelengths associated with these particles become incredibly tiny, and their energies become astonishingly high. At this point, the gravity produced by that energy bends space at scales smaller than the particles themselves. The calm separation we maintain between gravity for planets and stars and quantum mechanics for atoms and particles dissolves. Every bit of matter and energy now shapes space-time in a way that no existing theory can fully capture. This is why absolute hot is not just a number at the top of a chart. It marks the edge of where our current physical models can describe reality. Beyond it lies a region that would demand a theory of quantum gravity, a framework that can gracefully unite the rules of the tiny with the rules of the vast. People have been searching for such a theory for decades, but a complete, tested version has not yet arrived. There is something almost comforting in realizing that this limit is built into the fabric of things, the way the speed of light is built into the structure of space and time. You could imagine feeding more and more energy into some small region, hoping to push it past absolute hot. Long before you succeeded, the energy density would become so great that the region would pinch off into a tiny black hole. That black hole would evaporate extremely quickly through a process called Hawking radiation, releasing its energy again in a brief, wild flash. The system protects itself. It never calmly sits at a temperature beyond that limit. From this perspective, absolute hot begins to look like a kind of horizon, not a horizon of distance, but of description. When scientists talk about it, they are not just imagining a thermometer pegged at an absurdly large value. They are pointing at the spot where our stories about the universe need a new language. It is a reminder that even something as simple as asking, "How hot can it get?" can lead straight to the deepest unsolved questions in physics. The number itself, 2.55 times 10 to the power of 32 degrees Fahrenheit, barely fits in the mind. It is a 2, then a decimal, then more digits, and after that 32 zeros if you chose to write it the long way. When you first hear it, your thoughts may try to shrink it down to familiar scales. A hot summer afternoon, boiling water at 212 degrees Fahrenheit. A kitchen oven glowing at 500 degrees Fahrenheit, or the yellow white of a candle flame at around 1,800 degrees Fahrenheit. All of those belong to the same small neighborhood on the temperature ladder. Absolute hot is far beyond the far edge of that neighborhood. It can help to imagine a gentle staircase of temperatures just in your mind. Near the bottom is the air around you, perhaps somewhere between 50 and 90 degrees Fahrenheit. A bit higher is a warm bath around 100 degrees Fahrenheit. Higher still is water boiling at sea level at 212 degrees Fahrenheit. The hottest desert ground in places like Death Valley in California or the Lut Desert in Iran can reach around 130 to 160 degrees Fahrenheit on the surface. Already this is heat most of us would find unbearable. Above that, common experience falls away. A kitchen oven set to its highest setting can reach about 500 degrees Fahrenheit. A candle flame can glow near 1,800 degrees Fahrenheit. Fresh lava from a volcanic eruption can flow at temperatures between roughly 1,300 and 2,200 degrees Fahrenheit, turning rock into a slow, bright river that erases everything it touches. These are levels of heat that destroy living tissue almost instantly. Far above this, the sun waits. Its visible surface is around 10,000 degrees Fahrenheit, and the core where nuclear fusion occurs is near 27 million degrees Fahrenheit. In that core, atoms are stripped of their electrons, and bare nuclei are pressed together, releasing the energy that lights our days. Other stars are hotter. Some blue giants have cores with temperatures in the tens of millions of degrees. Supernova explosions, the deaths of massive stars, can briefly push temperatures in parts of space into the billions of degrees. Even more extreme are collisions between neutron stars, the crushed remnants of once massive suns. When these dense objects spiral together and merge, they can produce temperatures in the trillions of degrees Fahrenheit. In these brief, violent moments, elements heavier than iron, such as gold and platinum, are forged and thrown into space, eventually becoming part of planets and even part of our own bodies. Yet, when you set all of these against absolute hot, they remain on the lower rungs of the ladder. 1 trillion degrees Fahrenheit sounds impossible to grasp, but it is still many trillions of times cooler than the Planck temperature. The gap between them is not a step up, it is a sheer cliff, with the top shrouded in mist. Thinking about absolute hot, then, is less about picturing a specific furnace and more about contemplating a boundary. It is the point at which temperature, as a way of describing the jostling of particles, begins to lose its usual meaning. The motions are so energetic, the densities so high, that space and time themselves are drawn into the turmoil. Our equations, which serve us so well, from refrigerators to galaxies, begin to disagree with one another. Scientists sometimes give that earliest slice of cosmic history a name, the Planck epoch. It covers the first tiny fraction of a second after the Big Bang, shorter than 1/10 to the power of 43 seconds. In that interval, the universe was incredibly dense and incredibly hot, perhaps at or above the Planck temperature. All four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been merged into a single interaction. Space-time itself may have been foaming with quantum fluctuations, restless and unstable. And even so, this unreachable heat is quietly woven into everything close to you. Every atom in your body, every molecule in the air, every grain of dust, every planet, star, and galaxy was born from a universe that once burned near this unimaginable temperature. That makes the number feel less like something trapped on a chalkboard and more like an old memory written into matter itself. The first bright note in the long song of the cosmos struck when there was almost nothing but wild, blinding energy at a temperature so high we can only speak of it through theory. Letting that settle in can nudge your thoughts into strange corners. If absolute hot is a limit, what would it mean to try to get close to it on purpose? Could anyone ever build a machine for that? What would you even try to heat? At those extremes, there is no such thing as a stable object to warm up. Long before you reach the limit, atoms would fall apart, protons and neutrons would crumble, and even the idea of a neat, separate particle might stop making sense. You would be trying to pour energy into something that loses its familiar identity as soon as you begin. Because of that, scientists do not chase absolute hot by heating up blocks of metal or gases in a chamber. Instead, they use particle accelerators, giant machines like the Large Hadron Collider, that sling tiny particles around at speeds close to the speed of light and let them crash together. In those collisions, for a moment far shorter than a blink, in a region smaller than the width of a human hair, the energy becomes so concentrated that matter melts into a different state. In these experiments, nuclei of heavy atoms are smashed into each other until their protons and neutrons dissolve into their more basic pieces. The result is something called a quark-gluon plasma, a kind of hot, liquid-like soup where quarks and gluons move almost freely. The temperatures in this state can reach around 7.2 trillion degrees Fahrenheit. That is, a 7.2 followed by 12 zeros. It is hotter than anything that naturally exists on Earth, hotter than the core of most stars, and close to the conditions the universe had when it was only microseconds old. Even so, this is still far below the Planck temperature. Absolute hot sits roughly 30 trillion times higher on the scale. You could line up these achievements end to end, from the hottest furnace to the brightest supernova to the hottest collider event, and you would still be looking up a temperature cliff so steep that all the steps below blur together. The gap is not just wide, it almost feels like a missing realm. To feel how distant that realm is from daily life, it helps to return for a moment to the temperatures you already know with your skin. Think of standing near a hot stove, set to high. The metal glows, the air above it ripples, and the heat on your hand makes you pull away almost without thinking. A stove like that might reach about 500 degrees Fahrenheit. In a sauna, the air around you might be pushed up near 200 degrees Fahrenheit. Your skin prickles, your breathing grows shallow, and your body works quietly to shed the excess heat. Step outside on a clear day and let sunlight rest on your face. Even from about 93 million miles away, the sun's warmth finds you in seconds. Its surface is roughly 10,000 degrees Fahrenheit. If you could somehow stand there without being torn apart, you would not last long enough to admire the view. Yet from the point of view of physics, all of these numbers are close together, huddled in a tiny corner near the bottom of the cosmic thermometer. Inside the sun's core, where nuclear fusion turns hydrogen into helium and keeps our star shining, the temperature rises to around 27 million degrees Fahrenheit. That sounds huge, and it is enough to strip atoms down to bare nuclei and make them fuse. Other stars are more intense. Massive blue stars can harbor cores in the tens of millions of degrees. In their deaths, in explosions called supernovae, collapsing cores can reach temperatures in the hundreds of billions of degrees. In those brief, violent moments, atomic nuclei are forced together in ways normal stellar fusion cannot manage, building elements heavier than iron in a matter of seconds. There are even events where neutron stars, ultra-dense remnants of massive stars, collide. These crashes can heat small regions of space to trillions of degrees. At those temperatures, matter is pushed into states that strip away almost every structure we would recognize. Elements like gold and platinum are forged in these furnaces and scattered across the galaxy, eventually becoming part of worlds and living bodies. The most extreme temperatures we have actually measured, though, come not from nature, but from those carefully designed collisions in particle accelerators. The quark-gluon plasmas they create at around 7.2 trillion degrees Fahrenheit give us a tiny window into how matter behaved just after the universe cooled enough to form recognizable particles. They are like brief sparks that let us peek at an old fire long since faded. And still, compared to absolute hot, those sparks are cool embers. The Planck temperature is not just a taller mark on the same scale, it belongs to a different landscape. One way to picture this is to think of climbing a mountain that gradually turns into open sky. Near the base, the air is thick, trees grow, rivers run. Climb higher, and the air thins, plants shrink, and your breathing becomes strained. Above certain heights, like the summit of Mount Everest, you need special equipment just to stay alive. Go higher still, and you break into layers of the atmosphere where breathing is no longer a meaningful idea. Absolute hot is like that upper air on the temperature scale. At lower levels, adding heat changes matter in familiar stages. Ice warms and melts into water. Water heats and boils into steam. If you keep going, atoms are stripped and you enter the realm of plasma, where electrons and nuclei move freely. Higher still, in stellar cores, nuclei fuse, releasing enormous energy. At the highest temperatures we can probe, matter becomes a quark gluon plasma. But at the Planck temperature, you move beyond even this. You enter a region where space and time themselves are part of what is changing. Trying to draw all of this on a single graph is almost impossible. The difference between the warm air in your room and the boiling point of water is about 180 degrees Fahrenheit. In your everyday life, that jump from freezing to boiling feels huge. Yet on the full cosmic scale, it barely counts as a tiny step. If you tried to make a chart showing everything from room temperature up to the Planck temperature, you would face a choice. Either you compress the lower end so much that your everyday experiences flatten into a thin line, or you stretch the upper end so far that the top runs off the page. A gentler way to imagine it is to build a mental ladder where each rung is 10 times hotter than the one below. Start near 70 degrees Fahrenheit, the kind of mild air that feels comfortable on your skin. One rung up is 700 degrees Fahrenheit, the heat inside a commercial pizza oven. One rung above that is 7,000 degrees Fahrenheit, similar to the surface of some cooler stars or very hot flames. Above that, at 70,000 degrees Fahrenheit, metals would vaporize almost instantly. Keep climbing, 700,000 degrees, 7 million, 70 million, 700 million. At 7 million degrees Fahrenheit, you are in the domain of stellar coronas and hot plasmas in space. At 70 million and beyond, you are deep in the interiors of stars and in the aftermath of powerful explosions. Then come the billions, the tens of billions, the trillions. The rungs keep going, and somewhere far beyond the point where your intuition gave up long ago, the numbers finally approach the Planck temperature. By then, heat sounds less like a sensation and more like a label for an extreme state of reality. When scientists write about this in careful papers, they do not compare it to saunas, stoves, or summer days. They treat the Planck temperature as a fundamental limit, almost in the same spirit as the speed of light. You can imagine getting close to it in a calculation or in the early universe, but you cannot cruise past it and expect the same physics to work. It is not just an engineering problem, like building a stronger container. It is a boundary drawn by the structure of the theories themselves. This is where the two great frameworks of modern physics meet. On one side is quantum mechanics, the theory of the very small. It describes electrons, photons, quarks, and all the other tiny players using probabilities and wave-like behavior. In quantum mechanics, you never know everything about a particle at once. You talk about the chances of finding it here or there, with this or that energy. On the other side is general relativity, the theory of the very large. It describes gravity as the curvature of space-time, with massive objects bending that fabric and guiding the paths of planets, stars, and light. Most of the time, these two theories live in different neighborhoods. If you are calculating the orbit of a planet, you rely on relativity and do not worry about quantum uncertainty. If you are looking at the energy levels of electrons in an atom, you rely on quantum mechanics and can safely ignore the curvature of space-time. The domains barely touch in a way that causes trouble. Near absolute hot, that separation breaks down. At the Planck temperature, Each particle carries so much energy that its gravitational effect can no longer be ignored, even though it is tiny. Mass and energy are two sides of the same coin. So as you cram more energy into a small region, you also raise its effective mass. Enough energy packed into a tiny volume means enough gravity to noticeably warp space-time at subatomic scales. In that regime, quantum mechanics insists that you treat particles as fuzzy, probabilistic waves. General relativity insists that you treat energy and mass as sources of curved space-time. Trying to apply both sets of rules at once is like trying to speak two different languages in the same sentence. The mathematics we have today begins to spit out infinities, numbers that say some quantity would have to be infinitely large or small. In physics, infinities like that are usually a sign that a theory has been pushed past where it can be trusted. That is why the Planck temperature is described as a limit rather than just a very large value. It marks the point where our current descriptions of nature can no longer give clean answers. Below it, even at incredible heats, we can use known equations to make reliable predictions. At it or beyond it, we would need a new framework, a theory of quantum gravity that unifies quantum mechanics and general relativity into a single picture. Researchers have explored many ideas, string theory, loop quantum gravity, and others, but so far, no single approach has been confirmed by experiment. The idea of too hot in this deep sense is not just about discomfort or danger. It is about reaching a state where the usual background of our world, space, and time themselves start to behave in unfamiliar ways. At absolute hot, pouring energy into matter does more than make particles move faster. It begins to tug on the geometry they move through, blurring the line between what is being heated and the stage on which all events unfold. In that region, questions about temperature gently turn into questions about what space and time really are, and how they respond when pushed to their most extreme. If we stay with this picture a little longer, temperature itself starts to look different from the everyday version we carry around. In the world we move through, it feels like a simple measure of how fast particles are jiggling. But if those particles become energetic enough to bend the space they travel through and pull on the flow of time, then hot is no longer just about motion. It is also about geometry, the distances between particles, the way time passes from one tiny region to the next. The very shape of space-time all become part of what temperature means at the upper edge of possibility. The equations that describe this suggest that at extreme energies, space could stretch or wrinkle in ways we do not see in ordinary life. The fabric between particles might expand or contract. Time might tick at slightly different rates in different microscopic patches. These are not effects we can reach in a lab. Our machines are powerful, but they fall far short of the Planck temperature. Still, the mathematics that has guided us so well in gentler regimes hints that such strange behavior would appear when the energy density is high enough. One of the most startling possibilities in that regime is the appearance of tiny black holes. If you focus enough energy into a small enough volume, the gravity of that concentrated energy can become so strong that not even light can escape. In our universe, that is the condition for forming a black hole. At the Planck temperature, the energy packed into each microscopic region could be intense enough that miniature black holes form and vanish all the time. These would not be like the black holes we picture in space, swallowing gas and stars and lingering for billions of years. They would be fleeting, forming at subatomic scales and disappearing almost immediately. According to the idea of Hawking radiation, black holes are not truly black. They slowly emit particles and lose energy. For a tiny black hole, this evaporation would be almost instantaneous, happening in less than a trillionth of a second. Even though they are brief, their appearance and disappearance would change how energy flows through the system in a deep way. In such a wild environment, the usual meaning of temperature starts to fray. Temperature assumes that you can talk about a group of particles, each with some energy, and take an average. But if those particles are constantly falling into and emerging from microscopic black holes, or if space-time itself is fluctuating so violently that identities blur, it becomes hard to say what exactly you are averaging over. The idea of a stable collection of particles with well-defined properties might simply not apply in the way we are used to. Some attempts to describe physics at these scales suggest that what we call particles are not the most fundamental ingredients. In string theory, for example, the basic objects are tiny vibrating strings whose different modes of vibration appear to us as different particles. In loop quantum gravity, space-time itself is thought to be made of discrete loops or chunks. At energies near absolute hot, the familiar catalog of particles may dissolve into whatever structure lies beneath, whether strings, loops, or something else still waiting to be discovered. If that picture is right, then absolute hot is less like the top of a familiar thermometer and more like a doorway. On one side is the world we know how to describe, particles moving in space-time, exchanging energy, forming atoms, stars, and galaxies. On the other side may be a description where particles, fields, space, and time are just different expressions of a deeper, unified pattern. The Planck temperature marks roughly where the old language breaks down and the new one, whatever it is, needs to take over. Physicists care about this not just because it is a curious extreme. The early universe, in its first tiny sliver of a second, almost certainly passed through conditions at or near the Planck temperature. Whatever happened in that instant helped set the initial arrangement of matter and energy, the way space-time is curved on large scales, and the way the fundamental forces separated from one another. Understanding the physics of too hot could help answer questions about why the universe expanded the way it did, why matter exists in the amounts we see, and whether space-time has a smallest possible grain. We cannot recreate the full Planck-era universe in a laboratory, but we can look for hints. High-energy particle experiments push towards smaller and smaller scales, watching how matter behaves when it is shaken with more and more energy. Observations of extreme cosmic events, gamma-ray bursts, mergers of massive black holes, and other energetic flashes show us how nature behaves when vast amounts of energy are concentrated in small regions of space. And the cosmic microwave background, the faint glow left from the early universe, carries subtle patterns in its temperature and polarization that encode the physics of those first moments. The hope is that somewhere in all this information, faint fingerprints of Planck-scale physics are hiding. A tiny deviation in how certain particles interact, a slight twist in the polarization of ancient light, a pattern in the distribution of galaxies, all could be clues about the rules that took over near absolute hot. Until we find such clear signals, the Planck temperature sits on our theoretical horizon. We know its approximate value, we can write it down, and we can explore what happens as we approach it from below. But what lies beyond it remains an open, softly glowing question. To see why this question is so sharp, it helps to return to the foundation under everything we have been discussing. We use the word temperature easily. We check it in the morning to decide what to wear. We adjust it on a thermostat to make a room feel cozy. We read it on a weather app when planning a walk. Underneath all of those daily habits is a precise idea that physics uses in a very specific way. In its simplest microscopic form, temperature is a measure of the average kinetic energy of the particles in some substance. The atoms and molecules in your coffee, in the air around you, in the fabric beneath your hands, are never completely still. They shift, vibrate, rotate, and drift. In a solid, particles are bound to fixed positions relative to one another, but they still jiggle around their spots. In a liquid, they slide and flow past each other. In a gas, they move freely, bouncing around and colliding again and again. The hotter a material is, the faster this hidden dance tends to be. But average is a key word. At any moment, some particles will be moving more quickly than others, simply because of chance. Some will lag behind. Temperature does not tell you about the speed of any one particle. It tells you about the statistical behavior of the whole crowd. That is why you can have a room where a few air molecules are racing far above the average speed, and others are slower, yet still talk meaningfully about the air as, say, 72 degrees Fahrenheit. When you heat an object, you are adding energy to these internal motions. You might do it by placing it in contact with something warmer, letting energy flow across their shared surface. You might shine light on it, letting photons be absorbed and stir the particles inside. You might compress a gas, shortening the distance between particles and forcing them to collide more often and more violently. In every case, on average, the particles end up moving faster, and we interpret that as a rise in temperature. If you follow this idea all the way down instead of up, you reach another famous limit: absolute zero. In principle, if you could remove energy from these motions until there was none left to take, every vibration would quiet, every rotation would still, every drift would stop. That would be absolute zero, the lowest possible temperature, where the kinetic energy of the particles is at its minimum. In practice, quantum mechanics does not allow perfect stillness. There is always a tiny residual motion called zero-point energy. But conceptually, absolute zero marks the bottom, the place where motion cannot be reduced any further. On the other side, it might be tempting to think you can just keep adding energy forever. More energy means faster motion, and if there were no limits, temperature could rise without bound. The reason absolute hot appears at all is that two things eventually constrain this picture. One is that nothing can move faster than the speed of light. The other is that energy itself begins to curve space-time when enough of it is concentrated in a small region. Together, they tell us that at some point, motion alone cannot keep growing in the usual way, and temperature must be tied to deeper changes in geometry. There is also another, more abstract way to look at temperature, linked to the idea of entropy. In thermodynamics, entropy measures how spread out energy is and how many different microscopic arrangements correspond to the same overall state. Temperature can be defined as how the energy of a system changes when its entropy changes. Put more gently, temperature reflects a balance between how much energy is present and how many ways that energy can be arranged. This viewpoint is powerful because it lets us talk about temperature in situations where thinking about particles bumping around is not straightforward. The cosmic microwave background, a faint bath of light left from the early universe, has a temperature of just under 3 degrees above absolute zero when expressed in Kelvin. Black holes have a temperature associated with their Hawking radiation. Even a field of pure radiation, with no matter present, can be assigned a temperature based on how its energy is distributed over different possible states. Another subtle point is that temperature is always a property of a collection, not of a single object. A lone electron moving through space has energy, but it does not have a temperature by itself. Temperature becomes meaningful when you have many particles interacting, exchanging energy, and settling into some kind of statistical balance. That is one reason why states like the quark, life and gluon plasma produced in particle colliders are tricky to describe. They exist in such a tiny volume and for such a short time that talking about a smooth, well-defined temperature becomes more delicate. We do it, but always with care and approximations. People did not start out thinking this way. For most of human history, temperature was simply a feeling, the bite of winter air, the relaxing warmth of a fire. The first thermometers, built in the 17th century, gave us a way to attach numbers to those sensations, using landmarks like the freezing and boiling points of water. Only in the 19th century, with the development of kinetic theory, did scientists connect those numbers to the motions of atoms and molecules. Once that link was made, many puzzles began to clear. Gases expand when heated because faster-moving molecules push more strongly against their container. Solids melt and liquids boil because added energy lets particles break free from the bonds, holding them in one phase, or settle into new bonds in another. The rates of chemical reactions depend on temperature because reactant particles need enough energy to collide in the right way to climb over energy barriers. This microscopic picture has guided us reliably across a wide range of conditions. It even survives, with adjustments, into regimes that feel extreme. Air in a balloon at 70 degrees Fahrenheit and plasma in a fusion reactor at millions of degrees Fahrenheit can both be described using the same basic statistical ideas. It is only near the endpoints, close to absolute zero and close to absolute hot, that new layers of physics begin to dominate. Near absolute zero, quantum effects swell into prominence, and you see strange states like Bose-Einstein condensates, where many particles share a single unified quantum state. Near absolute hot, the gravity associated with energy itself becomes strong enough that space-time cannot be treated as a fixed background. Between those two extremes, temperature is one of the most versatile tools in physics. It ties directly into energy, entropy, and the laws of thermodynamics. The first law tells us that energy is conserved. When you add energy to a system, you can change its temperature or do work, or both. The second law tells us that, left alone, heat flows from hotter regions to cooler ones, and the total entropy tends to increase unless you put in effort to reverse that flow. These rules govern everything from making tea to running engines to modeling the interior of stars. There are even situations where our neat, intuitive sense of temperature gets flipped around. In certain special systems, you can end up with what physicists call a negative temperature. This does not mean colder than absolute zero. Instead, it means you have arranged things so that more particles occupy high-energy states than low-energy ones. In that case, adding energy can actually move the system toward a configuration that, by the formal definition, corresponds to a lower temperature. It is a reminder that temperature, though it feels simple, has layers of meaning that only fully unfold when you look carefully at energy and entropy together. When we place absolute hot in this broader context, its role becomes clearer. Temperature, as we use it, depends on being able to describe particles, their energies, and the space-time they inhabit in a consistent way. At the Planck temperature, those descriptions tangle. The background space-time may be fluctuating so violently, and the energies may be so high that the idea of a stable system with a well-defined average energy loses its footing. Absolute hot is thus not just the top value on a scale, but a threshold where our current language for motion, entropy, and geometry becomes too simple. The motion of particles, the spread of energy, the curvature of space-time, they are all tied together. As we follow temperature upward, each of these threads is pulled tighter. At ordinary conditions, motion dominates our picture. At more extreme conditions, entropy, radiation, and gravity all begin to share the stage. Eventually, the same speed limit that constrains any moving object, the speed of light in a vacuum, starts to shape how temperature can grow and how energy can be carried from place to place when everything is already moving almost as fast as it possibly can. Even in a system that is blisteringly hot, the messengers of that heat still have to obey that universal rule. Photons, the particles of light that carry radiant energy, are born moving at the speed of light and never go faster. As the temperature climbs toward the Planck scale, the particles in the system are not only racing, they are constantly creating and absorbing photons in a dense, restless exchange. The higher the temperature, the more intense this storm of light becomes, until the photons themselves are so energetic that their own gravity begins to matter in the story. At that point, the limit on speed becomes more than a simple cap on how fast things can move. It becomes part of a delicate conversation between relativity and thermodynamics. You cannot keep turning up the temperature the way you turn a dial on a stove without changing the very nature of what you are heating. The rules that work so well at ordinary temperatures gradually give way to new ones as energies rise, and motion alone is no longer enough to describe what is happening. From our everyday perspective, it is hard to feel what almost light speed really means. The jump from ordinary thermal motion to relativistic motion sits so far beyond our usual experiences that the numbers feel more like symbols than realities. In a room at a comfortable temperature, the average speed of air molecules is on the order of 1,000 miles per hour, fast enough to cross a continent in a few hours, but still laughably slow compared to light, which could circle the Earth 7 times in a single second. In the core of the Sun, protons move at a few percent of light speed, still with plenty of room before they approach the limit. Even there, the particles are, in a sense, jogging compared to what they could do in the most extreme conditions. As temperatures climb into the billions and trillions of degrees, though, particles begin to move so close to light speed that Einstein's relativity quietly takes over the bookkeeping. When a particle with mass moves faster and faster, each extra push of energy does less to increase its speed and more to increase its relativistic energy. You can keep feeding energy into it, but you get diminishing returns in velocity. Beyond a certain point, most of the added energy goes into making the particle heavier in the relativistic sense, and into thickening the energy density of the region it occupies. This is where the speed limit for motion starts to act like a speed limit for temperature as well. Temperature is tied to the average kinetic energy of particles, but there is only so much of that energy that can show up as simple motion. Once all the particles in a hot system are crowding close to light speed, extra energy has to express itself in other ways. In the creation of new particles and photons, in the growth of energy density, and eventually in the curvature of space-time itself near the Planck temperature. The energy packed into each small volume becomes so intense that space-time is forced to respond, no longer a quiet stage, but an active participant. In that regime, heating the system further does not just mean making the particles jiggle more violently. It means shaking the very medium they move through. Space-time may ripple and fluctuate. Quantum gravitational effects begin to dominate. The calm idea of a stable temperature, a single number that neatly summarizes the energies of a system, starts to feel uncertain, as if the system itself could not quite decide what it is. Long before we reach those heights, high-energy physics experiments give us faint previews of how matter changes as we push it harder. In particle colliders, heavy ions are accelerated to speeds extremely close to light speed and smashed together. In the tiny fireball that follows, matter melts into a quark-gluon plasma, a state where quarks and gluons move almost freely instead of being locked inside protons and neutrons. This plasma behaves like an almost perfect fluid with very low internal friction, and it shines its energy out as high-energy photons and gluons. The key point is that this state is not just hotter in the everyday sense. It is qualitatively different from any material you encounter outside of such extreme conditions. Relativistic effects dominate its behavior. The quark-gluon plasma flows more like a smooth, tightly coordinated liquid than a chaotic gas. The difference between this plasma and ordinary matter is a hint of how, as we push the temperature dial higher, we are not just climbing a familiar hill, we are walking into a new landscape where our usual intuitions about solids, liquids, and gases no longer apply. If you imagine turning that dial beyond even the hottest collisions we have achieved, the energies of the particles would grow until the wavelengths associated with their motion shrank toward the Planck length, about 1.6 times 10 to the power of minus 35 meters. That is an unimaginably tiny distance, far smaller than a proton, which itself is only about 10 to the power of minus 15 meters across. At scales like that, our usual ideas of position and trajectory may no longer make sense. Space-time itself may have a graininess or foam-like texture, and the notion of a smooth path for a particle becomes blurry. Seen this way, the speed limit of heat is not just about particles bumping up against the speed of light. It is about reaching a point where adding more energy stops being a matter of speed at all and starts to rewrite the fabric of reality. Energy piles up not in faster motion, but in curvature, in fluctuations, in the birth and death of tiny structures shaped by gravity and quantum rules together. Temperature, at that edge, is as much about geometry as it is about motion. There is a quiet symmetry between this upper limit and the opposite end of the scale. Near absolute zero, you run into quantum effects that prevent you from ever removing all motion. Even if you cool a system until it is as cold as you can possibly make it, the particles still have a faint, irreducible jitter called zero-point energy. Quantum mechanics will not allow a perfect, featureless stillness. Near absolute hot, you run into a different kind of impossibility. Relativistic and gravitational effects prevent you from simply increasing motion without bound. Once energies are high enough to twist space-time on tiny scales, hotter stops meaning what it used to mean. In both cases, the limits are not about our technology falling short. They come from the way the universe is built. The presence of the speed of light in this story is also why the Planck temperature is so closely linked to other Planck units, like the Planck length and the Planck time. All of these natural scales appear when you combine three fundamental constants: the speed of light, usually written as c, Planck's constant, which sets the graininess of quantum action, and the gravitational constant, usually written as g, which measures the strength of gravity. When you weave c, Planck's constant, and g together in different ways, you get natural units that do not depend on human choices like meters or seconds. The Planck length is the distance scale at which quantum and gravitational effects on space-time are equally important. The Planck time, about 5.4 times 10 to the power of minus 44 seconds, is the corresponding time scale, the smallest tick of time that makes sense in our current theories. The Planck temperature is the thermal face of this same combination. It is what you get when you ask, how hot would a system need to be for quantum mechanics, relativity, and gravity to all demand attention at the same moment? Another way to think about these units is to imagine that the universe had its own built-in ruler, clock, and thermometer, defined not by human convenience, but by the constants of nature themselves. The Planck length would be one mark on that ruler, the Planck time one notch on that clock, and the Planck temperature one mark on that cosmic thermometer. If any of the underlying constants were different, if light traveled more slowly, if gravity were weaker or stronger, if quantum effects turned on at another scale, all of these Planck units would shift as well. They quietly reflect the overall character of our universe. Written out, the Planck temperature is about 1.4 times 10 to the power of 32 Kelvin, or roughly 2.55 times 10 to the power of 32 degrees Fahrenheit. That is a 2.55 with 32 zeros after it if you were to write it the long way. The exact digits matter less than what the number represents. It is not a value we reached by slowly heating an object and taking its temperature. It is a value that falls out of the equations when we insist on treating the speed of light, the quantum of action, and the strength of gravity on equal footing, and ask what hot means in that context. As we climb the thermal ladder toward this scale, we pass through familiar phases: solids, liquids, gases, plasmas. We move into stellar interiors and supernova cores, into the brief flashes inside particle colliders, and beyond them into a region that no machine can touch. Each step upward adds new players and new behaviors. Molecules give way to atoms, atoms to ions, ions to bare nuclei, and finally, nuclei to quarks and gluons. Along the way, the story of heat gradually shifts from a tale about particles jostling to one about fields, geometry, and energy density. By the time we are even thinking about the Planck temperature, the simple picture of little balls bouncing around has been replaced by a more abstract one: quantum fields fluctuating, space-time curving and trembling, energy arranging itself in patterns that are hard to visualize. The speed limit on motion sets the background rhythm, but it is the gravitational consequences of extreme energy that bring the melody to its highest notes. In that light, the idea of absolute hot stops feeling like just an enormous entry in a table of constants. It becomes a signpost, quietly marking the place where our deepest physical principles meet. The quantum graininess of nature, the smooth bending of space-time, and the finite speed at which cause and effect can travel. The Planck temperature sits there at the top of the scale as the upper mark we keep in mind whenever we follow heat outward toward the point where the familiar rules begin to thin and a different description of reality waits just beyond our current reach. It is natural, then, to ask why this enormous number seems so absent from the universe we see. We do not find stars or galaxies glowing at 2.55 times 10 to the power of 32 degrees Fahrenheit. The reason is simple and deep at the same time. The conditions needed to reach that level of heat are so extreme that they cannot endure in the cosmos as it exists today. Inside stars, heat, pressure, and gravity lean against one another in a delicate balance. The temperature in their cores is high enough to keep nuclear fusion running, but not so high that the star tears itself apart at once. Even in supernova explosions, where a massive star's core collapses and rebounds in a violent flash, the peak temperatures reach hundreds of billions or trillions of degrees and then fall as the material expands and cools. The Planck temperature sits far above all of this, beyond any stable stellar process. On Earth, in particle colliders, we can create tiny droplets of matter so hot that the hearts of stars would seem cool. These quark-gluon plasmas reach into the trillions of degrees and exist for times so short we can barely name them. The energy is packed into a region smaller than a grain of dust and then spreads out almost at once. And even then, we are still many trillions of times below the Planck scale. As far as we know, the universe has truly passed through the Planck temperature only once, in its earliest instant. Since then, nothing has recreated those conditions in a sustained way. There is also another sense in which this number is a one-time thing. At the Planck temperature, the concept of temperature itself starts to unravel. The energy density is high enough that tiny black holes could form out of quantum fluctuations, space-time ripples and jitters, and the forces we treat as separate may already have merged into a single interaction. In such a regime, talking about the average kinetic energy of particles is a little like trying to talk about the average depth of puddles during an earthquake, when the ground itself is rising and falling. The reference frame you are using refuses to stay still. The usual landmarks of physics, individual particles, separate forces, a smooth background of space and time, are disturbed all at once. That is why the Planck temperature is more than just an endpoint on a scale. It is a signpost pointing toward a landscape where our present ideas need to be rebuilt. Above that signpost, the familiar map of physics fades. The regions we know, electromagnetism, nuclear forces, classical gravity, may give way to terrain we have never explored. In that sense, the Planck temperature is a boundary in the space of theories as much as it is a limit in the physical universe. Our equations gesture toward it, but do not fully describe what lives beyond. There is something quietly humbling in the way this number appears. It comes from three constants that we measured in very different ways. The speed of light was pinned down by studying electromagnetic waves and the behavior of light itself. Planck's constant emerged from the study of quantum phenomena, how atoms emit light in discrete colors, how electrons behave in metals, how tiny packets of energy called quanta show up in experiments. The gravitational constant grew out of measurements of the attraction between masses, from careful torsion balance experiments in laboratories to observations of how planets and moons move. At first glance, these constants seem to belong to separate stories, one to light and radio waves, one to the quantum behavior of atoms, one to the slow pull that shapes orbits. Yet when they are combined, they give us the Planck units, a natural set of length, time, mass, and temperature that seem to whisper where quantum effects, gravity, and the speed of light all meet. Limits like this are not just walls, they are clues. The Planck temperature is telling us that there is something about the way energy, space-time, and quantum uncertainty talk to one another that sets a maximum for heat. Understanding why that maximum exists in detail would almost certainly teach us something deep about the structure of reality. In that way, 2.55 times 10 to the power of 32 degrees Fahrenheit is not only an upper mark on a thermometer, it is also a destination on a long, careful journey of understanding. Even if we cannot reach that value in a laboratory, we can edge toward it indirectly. Particle accelerators push matter to higher energies and show us how quarks, gluons, and other particles behave as the temperature climbs. Astrophysical observations, such as gamma-ray bursts, flares near black holes, and the mergers of neutron stars, reveal how nature handles extreme concentrations of energy on vast scales. Cosmology, with its measurements of the cosmic microwave background and the distribution of galaxies, works backward in time to reconstruct the conditions of the very young universe, when everything was much hotter and denser than it is now. Each of these paths brings us closer to the edge. They do not put us at the Planck temperature, but they help trace the outline of the physics leading up to it. If the speed of light is a kind of cosmic speed law, limiting how fast information and influence can move, then the Planck temperature is like its thermal companion. It is the top gear of the universe's engine, the setting at which the known machinery of physics is running as hard as it possibly can. To push beyond that would require a different sort of engine, a new framework that we do not yet have. This gives the Planck temperature a different flavor from other big numbers in science. We are used to millions, billions, and trillions describing quantities we can still picture in some loose way. Here, the size of the number is really telling us where our present description of reality runs out, and another, still unknown description has to take over. To approach what might lie on the other side, we have to adjust the way we picture the basic ingredients of nature. When we talk about particles like electrons, quarks, or photons, it is tempting to imagine tiny billiard balls rushing through space and bouncing off each other. Modern physics paints a different scene. In the framework we use today, particles are excitations of underlying quantum fields. Each type of particle has a corresponding field spread throughout all of space: an electron field, a photon field, quark fields, and more. Space is not an empty stage. It is filled with these invisible, ever-present fields. You can imagine each field as a smooth, elastic sheet stretching everywhere. A particle is like a small ripple or localized wave moving across that sheet. An electron is a ripple in the electron field. A photon is a ripple in the photon field. Even when there are no particles present in the everyday sense, the fields themselves are never perfectly flat. Quantum mechanics insists on small fluctuations, tiny bursts of activity that flicker in and out, because uncertainty is part of how reality is built. At ordinary and even stellar temperatures, These fields are stable enough that we can treat them separately. The electron field reliably produces electrons with a certain mass and charge. The quark fields combine into protons and neutrons, even inside hot stars or in the brief flashes inside colliders. Each field keeps its own identity, and the particles that arise from them follow well-tested rules. As the energy scale climbs toward the region associated with the Planck temperature, that clean separation becomes less certain. The energy of individual excitations can grow so large that the boundaries between fields may begin to blur. The categories electron, quark, or gluon may stop being truly fundamental. The quantum fields themselves might merge into a more unified entity, with today's variety of particles emerging only when the universe is cooler and calmer, the way distinct colors of light appear when a prism spreads a single white beam into a spectrum. This idea fits with what we already suspect about the fundamental forces. Today, we recognize 4. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. At energies we can reach in colliders, we have already seen electromagnetism and the weak force merge into a single electro-weak interaction. Some grand unified theories suggest that at higher energies, the strong force joins them. The Planck temperature lies far above these scales, at a point where gravity itself may fit into the same unified picture. If that is so, then in the earliest instance after the Big Bang, there may have been a time when there was only one basic interaction with all the forces we know now, just different aspects of it. As the universe expanded and cooled, this symmetry could have broken in stages, leaving behind the separate forces and particle types we see today, like patterns that appear as a hot liquid solidifies. Quantum field theory, as we normally use it, assumes a calm background spacetime for all of this to happen on. The fields live on a smooth stage. General relativity, in contrast, describes how mass and energy bend that stage, curving space-time continuously. Near the Planck temperature, these two pictures refuse to stay separate. The quantum fields cannot be treated independently of the geometry they inhabit, and the geometry cannot be described without the violent fluctuations of the fields. In such an environment, quantum fluctuations are no longer tiny background ripples. Some can become dense enough to warp spacetime on very small scales, even collapsing into microscopic black holes that live for only an instant before evaporating in bursts of high-energy particles. Instead of a quiet vacuum, you would have something more like a boiling quantum fluid. Horizons would form and vanish. Fields would surge and relax. The distinction between particle, field, and geometry would blur into a single, restless structure. In that structure, the neat idea of a particle with a fixed mass, charge, and spin might not apply in the usual way. What exists instead could be transient disturbances that resist being placed into any of the categories that make up today's particle tables. Some versions of string theory imagine that all particles are different vibrational modes of tiny, one-dimensional strings. At low energies, only a few of those modes are active, giving rise to the limited set of particles we see. Near the Planck temperature, many modes could be excited at once, turning the particle zoo into a dense chorus of overlapping vibrations. Other approaches, like loop quantum gravity, suggest that space-time itself is built from discrete loops, or quanta. At the Planck scale, these loops would be as important as the fields they contain. and space and field would no longer be separate ideas. We do not yet know which of these ideas, if any, is closest to the truth, but they all hint in the same direction. Near the Planck scale, quantum fields, particles, and space-time can no longer be peeled apart. They become different faces of one underlying reality. The early universe, in its first tiny fractions of a second, was probably the only time this regime existed everywhere at once. Now we look for its echoes. The faint patterns in the cosmic microwave background, the spread of galaxies across space, and the behavior of structures on the largest scales all carry subtle traces of the physics that ruled just after the Planck era. By reading those traces more carefully, cosmologists hope to glimpse how the quantum fields behaved on the edge of this unification, and how the universe slowly relaxed from that wild beginning into the calmer, cooler state we are part of now. As we follow these ideas outward, all of them keep circling back to the same question: what is really happening in the deep structure of the quantum fields that fill the universe? Those fields give us particles, forces, and the familiar matter around us. But there is another layer waiting just beyond them, because the Planck temperature is not only about fields straining to hold their shape, it is also about gravity stepping fully into the scene, not as a quiet background, but as an equal partner reshaping everything. In everyday life, gravity feels like the main character. It keeps your feet on the ground, holds the oceans to the earth, makes planets move in their orbits, and pulls galaxies into clusters. Yet when we zoom down to the subatomic world, gravity almost disappears from the conversation. Compared to the strong nuclear force that glues nuclei together, the electromagnetic force that makes atoms and light behave, and even the weak force that governs certain kinds of radioactive decay, gravity is so faint that we can usually ignore it when talking about individual particles. That quietness does not last forever. Energy and mass are two sides of the same coin, and as particles gain more and more energy, their gravitational influence grows. At modest energies, a single particle's gravity is tiny, too small to matter in any collision. But as we push toward the Planck temperature, the energy carried by each particle becomes so large that its ability to curve space-time is no longer negligible. Gravity moves from the background to the foreground. It stops being a soft whisper and becomes part of the main dialogue. Einstein's general theory of relativity is the language we use for gravity. In that picture, gravity is not a simple pull between masses. It is the bending of space-time by energy and matter. A planet like Earth curves the space-time around it, and that curvature guides how other objects move. Usually, to see a clear effect, you need a lot of mass or energy, a star, a black hole, a galaxy. But near the Planck scale, even a single highly energetic particle can noticeably bend the space-time in its immediate neighborhood. Here is where the trouble begins for our current theories. Quantum field theory, which describes particles and their interactions, is built on the assumption that space-time is a steady, smooth background. You put fields on that background and calculate how they behave. General relativity, in contrast, treats space-time as flexible, changing in response to energy and momentum. When the energies involved are immense, these two views collide. If particles are energetic enough to distort space-time, and that distorted space-time in turn affects how particles move and interact, you get a feedback loop that neither theory alone was designed to handle. At the Planck temperature, this feedback loop is not a tiny correction. It dominates. Quantum theory expects a well-defined geometric stage. Relativity expects a continuous, gently curving fabric. Quantum uncertainty insists that at very small scales, that fabric cannot stay perfectly smooth. It has to jitter. When you combine all of that with enormous energy densities, the calm separation of roles we rely on at lower energies breaks down. The result, at least in our current math, is a tangle of infinities and contradictions, a sign that we have pushed our tools beyond their reliable range. One dramatic picture that emerges from this tangle is the idea of microscopic black holes forming all the time at such high energies. General relativity gives a simple rule of thumb. If enough energy is concentrated in a small enough region, it will form a black hole. At the Planck temperature, particle wavelengths are so short and their energy is so intense that many fluctuations meet that condition. These black holes would be minuscule, far smaller than atoms, but their gravity would be fierce in their tiny domains because of quantum effects, especially the process known as Hawking radiation. These tiny black holes would not last long. They would evaporate almost instantly, turning their energy back into particles and radiation. Imagine space-time as a kind of seething foam, dotted with these fleeting horizons that appear and vanish faster than we can comfortably picture. Instead of a smooth, continuous fabric, you get something more like a boiling surface, restless and full of tiny, short-lived structures. In such an environment, even the idea of vacuum changes. In quantum field theory, the vacuum is the lowest energy state of a field, not truly empty, but as calm as the field can be, with only small quantum jitters. In general relativity, vacuum means empty space-time, with no matter and no curvature, a flat stage. At the Planck scale, those two notions collide. The vacuum might be neither empty nor flat. It could be a dense, constantly changing quantum gravitational medium, often described with the image of space-time foam. In that foam, light might not travel in perfectly straight lines. The idea of a single exact speed of light might be softened at the tiniest scales, and the link between cause and effect could become fuzzier than we are used to. All of this also affects how we think about temperature in such a regime. At familiar energies, temperature is about the average kinetic energy of particles. You can talk about a bulk property for a gas, a metal, or a plasma, and different observers agree on what that temperature is once they correct for motion. In strong gravitational fields, even in more ordinary situations like near a massive star or black hole, time runs at different rates depending on where you are. Clocks deeper in a gravitational well tick more slowly than clocks far away. That means that temperature, which is tied to energy and time, can become slightly observer-dependent. Near the Planck temperature, this effect becomes more pronounced. The curvature of space-time is so extreme and so rapidly changing that two observers in different locations or following different paths might not agree on what temperature means for the same region of energy. The pressure and stress in the system, not just its energy, contribute to how space-time curves. In a gas of particles moving close to the speed of light, the pressure can be huge, and at the Planck scale, both energy density and pressure shape space-time strongly. Gravity no longer just pulls. Under the right conditions, it can help drive rapid expansion as well. This kind of behavior is central to our ideas about the very early universe. There is a period called the Planck epoch, a time so close to the beginning that we measure its duration in Planck times. 1 Planck time is about 5.4 times 10 to the power of minus 44 seconds. The Planck epoch is thought to have lasted around that long, an instant so brief that if you tried to compare it to a single blink, an unimaginable number of Planck times would pass within that blink. During that fleeting interval, the temperature of the universe was at or above the Planck temperature. This was not heat, as we feel it when we sit near a fire or stand in the sunday. It was an energy density so intense that space-time, fields, and whatever lay beneath them were in constant, violent motion. Matter as we know it did not exist. Even the concept of a well-defined particle may have been meaningless, because the quantum fields that normally give rise to particles were themselves woven into the turbulent geometry. In those conditions, the four forces we talk about today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been merged into a single interaction. The differences that make them feel separate now would not yet have appeared. As the universe expanded and cooled, this unified interaction could have undergone a series of symmetry breakings, splitting into the distinct forces we observe. A gentle analogy is to imagine the universe at the beginning as a perfect, symmetric crystal. At the highest temperature, that symmetry is intact. As it cools, tiny imperfections and changes appear, and the crystal's properties shift. Except in this case, the crystal is space-time and the fields living on it, and the changes affect everything, everywhere. Each symmetry breaking would release energy, alter the behavior of the fields, and change what kinds of particles and forces are possible. The energy density during the Planck epoch is almost impossible to picture. Today, the most violent cosmic processes we see, gamma-ray bursts, merging black holes, the cores of supernovae, do not come close. Back then, the entire observable universe was a furnace beyond any comparison, and it was not still. Space itself was expanding, perhaps in a way so rapid and dramatic that our ordinary notions of distance and time do not quite apply. There is good reason to think that quantum fluctuations during this early phase were amplified by gravity. Tiny differences in density, originally just random quantum ripples, could have been stretched and grown by expansion. Those tiny seeds would later become the large-scale structures we see now: galaxies, clusters, and the web-like pattern of matter spread across the cosmos. The faint variations in the temperature of the cosmic microwave background, small differences of only a few 10,000ths of a degree, are likely the fossil record of those first ripples. This is where the interplay between quantum mechanics and gravity becomes inescapable. We cannot describe the Planck epoch using only quantum field theory, because space-time was not a fixed background. We cannot describe it using only general relativity, because quantum effects were dominant. We need a theory that merges them, a true quantum theory of gravity. We do not have that theory yet, but we can sketch some possibilities. Some ideas suggest that during the Planck epoch, tiny, short-lived black holes formed from especially dense fluctuations and then evaporated almost immediately, sprinkling energy back into the surrounding soup. Other ideas propose that the universe went through a kind of phase change from a pre-geometric state into the space-time we know, with the Planck temperature marking the threshold. There are even speculations in which our universe might have emerged from the collapse or bounce of a previous universe, with the Planck era serving as a moment of transformation. What we can say with some confidence is that as soon as the temperature dipped below the Planck limit, the universe entered a new regime. The foam-like behavior of space-time began to calm. On average, the forces started to separate into distinct roles. Conditions became tame enough for particles to have stable identities and for temperature to take on its more familiar statistical meaning. This cooling did not take long in absolute terms, fractions of a second. But in that narrow window, the foundations for everything that followed were set. Every galaxy, every star, every atom in your body, and every chemical bond that makes your world possible traces its history back to choices made in that early, hot state. If the constants of nature had slightly different values, or if the sequence of symmetry breakings had unfolded in another way, the universe could look very different, or might not allow complex structures at all. And this was not something that happened in one small corner of space. Every point in the region we can see today was once part of the same dense, blazing quantum gravitational mixture. That shared origin is why the universe looks so similar in all directions on the largest scales, a property called isotropy. The smoothness of the cosmic microwave background, apart from those tiny ripples, is one of our strongest hints that everything we observe grew out of a single, extremely hot beginning. We cannot recreate the Planck epoch, but we can study it indirectly through that ancient light and through high-energy experiments that probe the nearest accessible rungs below the Planck temperature. Bit by bit, those clues help us refine our picture of what gravity, quantum fields, and temperature were doing in that first instant when the universe was, for a moment, as hot as it can ever be. When we think back to that first instant, the hottest moment the universe has ever known, there is a quiet pull in it. It is both an ultimate extreme and an origin point. For a brief sliver of time, the temperature of the cosmos was not just a number on some imaginary scale, but a boundary between what we can describe and what we can only gesture toward. In that flash, space, time, and energy began to take on the shapes that would eventually become stars, atoms, and people lying awake at night, wondering how it all began. It is easy to picture absolute hot and absolute zero as simply the two ends of one long glass thermometer, one end unimaginably high, the other unimaginably low, and somewhere in the middle, the familiar weather of everyday life. But the universe is more subtle than a straight line. These two extremes are not just opposite values, they are opposite ways for reality to behave when you push it as far as it can go. Absolute zero, 0 Kelvin, or about minus 459.67 degrees Fahrenheit, is the lower extreme. It is the point where, in classical thinking, you have removed all possible thermal energy from a system and all motion would stop. In practice, quantum mechanics never quite allows that stillness. Even at absolute zero, particles keep a faint, irreducible motion called zero-point energy, a tiny jitter demanded by the uncertainty principle. You can get astonishingly close in the lab, within billionths of a Kelvin, but you can never cross that last tiny gap. The barrier is built into the rules. You cannot have perfect stillness and perfect knowledge of a particle's position at the same time. Absolute hot is the mirror opposite. It is not about taking energy away, but about adding so much that the idea of motion in the usual sense begins to lose meaning. Near the Planck temperature, where we are talking about roughly 2.55 times 10 to the power of 32 degrees Fahrenheit, particles are already moving at speeds very close to the speed of light. Pushing them further does not make them significantly faster. Relativity will not allow it. Instead, the extra energy starts to change what the particles are, how the fields beneath them behave, and how space-time itself responds. The wall here is not the same as at the cold end. It is not set by quantum uncertainty alone. It comes from the combination of relativity, quantum mechanics, and gravity. Beyond a certain energy density, space-time cannot just sit there passively while you pour in more heat. It bends, fluctuates, and reacts so violently that the simple picture of particles bouncing in a smooth container stops working. You can think of the two extremes as limits on opposite kinds of effort. At absolute zero, the limit is about what you cannot take away. You cannot strip out the last trace of quantum jitter. At absolute hot, the limit is about what you cannot add. You cannot keep injecting energy indefinitely without triggering a change in the very rules that define temperature. In one direction, the smallest possible motions refuse to vanish. In the other, the medium you are trying to energize refuses to stay in the form you are demanding. Near absolute zero, the world becomes strangely ordered. Quantum effects like superfluidity, superconductivity, and Bose-Einstein condensation rise to the surface. Collections of atoms can fall into a single shared quantum state, moving in perfect step, with resistance to flow vanishing and waves overlapping neatly. The colder you go, the more coherent and unified the system becomes, like a choir singing a single, pure note. Near absolute hot, the opposite happens. Order dissolves, but not as simple disorder. It is not just a gas of particles bouncing randomly. It is a deeper kind of chaos, in which the very categories of particle and force begin to blur. Gravity becomes as strong as any other interaction at tiny scales. Space-time foams and ripples, and the underlying structure of the universe may be flickering and unstable. At the cold end, everything narrows toward a neat, shared pattern. At the hot end, the patterns themselves start to melt. The ways we approach these limits in practice reflect this difference. To move toward absolute zero, you have to remove energy as gently and completely as you can. You isolate atoms from their surroundings, trap them in carefully shaped fields, cool them with lasers that nudge away their motion, or let the most energetic ones escape so only the slowest remain. It is a process of quieting, refining, trimming away excess until only the lowest possible motions are left. To move toward absolute hot, even just in theory, you have to do the opposite. You must pour energy in on a colossal scale, compress matter to astonishing densities, or smash particles together at nearly the speed of light. Nature did this for us in the early universe, when everything was packed into a tiny, furious volume. We imitate it in a very small way when we run particle colliders at full power. It is not a process of calming, but of overfeeding, giving the system so much energy that its familiar structure breaks down. Both extremes remind us that temperature is not just a number glowing on a digital display. It is tied to how matter and energy arrange themselves under stress. At absolute zero, motion does not vanish, yet that residual motion is so constrained that systems can fall into perfectly coherent, delicate states we never see at room temperature. Near absolute hot, motion does not simply increase without bound. Instead, the energy begins to reshape space-time and blur the distinction between matter, radiation, and geometry. In both cases, the everyday picture of temperature as how fast things move is only the beginning of the story. There's a pleasing symmetry hiding there. One limit marks a world of maximal stillness that cannot be completely reached. The other marks a world of maximal agitation that cannot be sustained. One is approached by removing energy, the other by adding it. One runs into the impossibility of perfect order, the other runs into the impossibility of holding together boundless chaos. And beneath both sit the same small set of constants, Planck's constant, which sets the scale of quantum effects, the speed of light, which caps motion and information, and the gravitational constant, which tells space-time how strongly to curve in response to energy. In that sense, absolute zero and absolute hot are like bookends for everything that can happen thermally in our universe. Every warm breeze, every star's glow, every chemical reaction and living process occurs in the vast middle, between a stillness we can never quite reach and a heat that would unmake the meanings of matter in space. The values of these extremes are not arbitrary. They are fingerprints of the way our universe is built. Change the constants, and the bookends would shift, along with all the stories between them. Thinking about both ends together makes it easier to see how fragile and special the conditions of ordinary matter really are. At the temperatures we live with, matter is well behaved. An atom of hydrogen carries 1 proton and 1 electron. Carbon has 6 of each. Protons and electrons have stable masses and charges. Quarks hide quietly inside protons and neutrons. The forces that bind them, the strong force inside nuclei, electromagnetism between charges, are firm enough to hold structures together, but gentle enough to allow a huge variety of combinations. This reliability is why chemistry works, why solids and liquids and gases keep their character, why rocks feel solid and air feels light. It all depends on the fact that we are living in a moderate band of the temperature scale, unimaginably mild compared to the upper limit. As the temperature rises, those categories begin to loosen. Heat a material to thousands of degrees, and atoms start losing their grip on their electrons. Electromagnetic attraction can no longer keep electrons bound to nuclei against the jostling of thermal motion. What you get is plasma, a sea of free electrons and bare nuclei. Plasmas fill stars and glow in lightning. They are already a different state of matter, more collective and fluid, guided by large-scale electric and magnetic fields. Push further into the millions of degrees found in stellar cores, and plasma is the norm. Push farther still into the trillions of degrees achieved in the hottest collider experiments, and even protons and neutrons cannot stay intact. The strong nuclear force, which usually traps quarks snugly inside those particles, is overwhelmed by the thermal energy. Quarks and gluons spill out into a quark-gluon plasma, a kind of soup in which they move more freely. Physicists have created quark-gluon plasmas in particle accelerators for fleeting moments. Those droplets are tiny and short-lived, but they give us a snapshot of what the universe was like around a millionth of a second after the Big Bang, when everything everywhere may have been in that state. Even here, though, we are still working with quarks and gluons as defined by our current theories. Beyond that, as we continue upward in energy in our imagination, the structure may loosen further. At even higher temperatures, well before the Planck scale, the strong force and the electroweak force might unify into a single interaction, as some grand unified theories suggest. The fields that give particles their masses could behave differently. Particles and antiparticles might be more easily created and annihilated, swapping identities in a constant dance. The familiar zoo of particles could shrink into a smaller set of more fundamental modes that only reveal themselves when the system is excited enough. Near the Planck temperature, this gradual identity crisis reaches its peak. The quantum fields that underlie all particles may no longer be neatly separate. Instead of a distinct electron field, photon field, quark fields, and so on, there could be a single, more primitive structure whose different patterns of vibration or configuration show up at lower energies. As all the separate fields we know, in that regime, the usual divide between matter and forces may not apply. There may simply be energy and geometry, and whatever basic ingredients weave them together. This is the ultimate version of melting, not just ice into water or nuclei into quarks, but the melting of the very definitions we use: particle, field, force, space. It is tempting to think of that state as pure disorder, but there is another way to see it. At the very highest energies, the symmetries of nature may be most complete. The universe might have been simplest in a hidden way when it was hottest, with all its possibilities wrapped into a single, symmetric state. As it cooled, that symmetry broke in stages, and each break allowed new structures, new particles, and new forms of complexity to appear. Viewed through the lens of information, each type of particle, carries information about how it can behave, what it can join with, what forces it feels, what patterns it can form. Near the thermal ceiling, those labels might fade. Instead of a library full of separate volumes, you have a blank page containing the potential for all of them at once. As the universe cooled, that blankness unfolded into the rich catalog we see now. Tracing how matter gradually loses its identity as temperature rises is one way to understand why it has the identity it does at gentler scales. The way things fall apart at the top end quietly explains why they hold together here, in the middle, where we can reach out, touch a solid surface, and trust that it will still be there in the morning while the deeper, hotter story continues just beyond the edge of what we have yet explored. If we could somehow trace, step by careful step, how the universe cooled from a single unified state into the rich pattern of particles and forces we know as the Standard Model, a lot of long-standing questions would suddenly feel less mysterious. We would understand why particles carry exactly the masses they do, why each force has its particular strength, and why some symmetries survive while others are quietly broken. It would be like having the missing pages of a story we have been reading from the middle. The difficulty is that we can only reach those early conditions for the briefest instance and at a great distance from the true extremes. The quark-gluon plasmas we create in particle colliders are tiny and short-lived, little sparks compared to the furnace of the first moments. Anything closer to the true grand unification scale or to the Planck temperature is far beyond what we can reproduce. So most of what we know about this identity crisis of matter comes indirectly from the way the universe looks now, from the behavior of high-energy cosmic rays, and from the mathematics of models that we try to keep as honest as we can. It may even be that the very word matter only properly belongs to the cool, expanded universe we live in. For the first fraction of a second, when the temperature was at its peak, the cosmos could have been something else entirely, a state where the usual separation between matter and energy, particle and field, had not yet emerged. That world is gone, but its fingerprints are everywhere, in the forces that hold atoms together, in the patterns of galaxies, and in the faint microwave afterglow spread across the sky. As we follow the idea of temperature upward toward the Planck scale, we eventually feel something like the edge of our own intellectual map. Not a physical wall, but a boundary in understanding, where the tools we use begin to disagree with one another. On one hand, we can calmly write down the value of the Planck temperature, about 1.4 times 10 to the power of 32 Kelvin, or roughly 2.55 times 10 to the power of 32 degrees Fahrenheit. We can show how it falls naturally out of combining the speed of light, Planck's constant, and the gravitational constant. The arithmetic feels solid, but knowing how to calculate the number is not the same as knowing in detail what a universe at that temperature is actually like. At lower energies, we have two great frameworks that work beautifully in their own territories. Quantum field theory describes particles and forces on tiny scales, assuming that space-time is a smooth, fixed background. General relativity describes how space-time itself curves and flows, assuming that the objects moving through it can be treated classically, not as fuzzy quantum waves. In most places, the assumptions behind these theories do not collide. For atoms and molecules, we can ignore gravity. For planets and galaxies, we can ignore quantum fuzziness. Near the Planck temperature, those safe separations vanish. Space-time is no longer smooth. Quantum fluctuations wrinkle it. The background is no longer fixed. Enormous energy densities distort it, even on microscopic scales. Quantum field theory wants a steady stage to perform on. Relativity insists that the stage is constantly being rebuilt by the actors. When both the fields and the geometry are fluctuating together, the equations fold back on themselves. Attempts to calculate simple things can explode into infinities that no longer cancel neatly. The tricks of renormalization that work so well at lower energies begin to fail. That is the first wall, the mismatch between our two best stories about reality. Physicists have spent decades trying to build a bridge between them. String theory replaces point-like particles with tiny one-dimensional strings, whose vibrations give rise to the particles and forces we know, including gravity. Loop quantum gravity tries to quantize space-time itself, imagining it as woven from discrete loops or chunks at the smallest scales. Other ideas, like causal dynamical triangulations and related approaches, explore different ways to make space-time granular and quantum. Each has its strengths and its puzzles. None has yet delivered a complete, experimentally confirmed picture of what truly happens at the Planck temperature. The second wall is more practical. Our experiments cannot climb anywhere near that high. The hottest conditions we create in colliders reach trillions of degrees, enough to make quark-gluon plasmas for a fleeting moment. But the Planck temperature is 20 orders of magnitude higher in energy. To bridge that gap, we would need to increase particle energies by something like a trillion, and not just for a single particle, but for an entire collection reaching thermal equilibrium. No machine we can realistically imagine, even spread across the scale of a solar system, could supply that energy. So we rely on indirect clues, patterns in the cosmic microwave background, the distribution of galaxies, and the spectra of high-energy cosmic rays. A third wall is quieter and a little unsettling. It has to do with the language we use. Our vocabulary, particles, waves, forces, space, time, is built from experiences at human scales and from experiments in relatively gentle regimes. Near the Planck temperature, those may simply not be the right building blocks for a description. The universe might not be composed of particles in any sense that matches our mental picture. Space and time might not be continuous or even fundamental. They could be emergent, appearing only when the underlying ingredients organize themselves in the right way, the way temperature itself emerges from the motion of countless molecules. If that is true, then trying to talk about Planck scale physics using only our current terms is like trying to explain quantum mechanics purely with the language of billiard balls and clockwork gears. You can make analogies, but the reality keeps slipping through. The stubborn infinities that show up in our calculations near this regime are another hint. At more modest energies, we tame infinities in quantum field theory with renormalization, folding them into redefined masses and charges that match what we measure. Near the Planck scale, gravity makes those infinities worse, and the usual methods no longer neatly repair the theory. When a calculation that should yield a finite answer instead gives infinite again and again, it is a sign that the questions are being asked in the wrong framework. Because of all this, the Planck temperature is less a simple hottest point and more a marker. Here, our present theories run out of breath. It does not mean that physics itself fails, only that the physics we know is a limited case of something larger. Finding that larger theory is not just about describing one exotic corner of the temperature scale. A working theory of quantum gravity would likely connect the tiniest scales to the largest, joining our understanding of particles with our understanding of cosmic evolution in a single, more continuous story. There is a small irony hiding in all of this. At room temperature, we can describe the behavior of gases, liquids, and solids with high precision. Near absolute zero, we can predict how ultra-cold atoms will form delicate quantum states, matching experiments to many decimal places. But at the very top of the scale, our predictive power falls apart. It is almost as if the universe has tucked its deepest rules behind a curtain of heat, visible only as an outline drawn by indirect clues. In the meantime, the Planck temperature waits on our charts like a small, dense annotation at the top of the scale, a quiet label saying, "Beyond this, the current map is incomplete." It is not a warning to turn back so much as an invitation to think differently. We cannot reach that regime with machines, but we can approach it with thought, with mathematics, with the traces written in ancient light and high-energy particles. And as we follow those traces, through supernova cores, around black holes, along the paths of the most energetic cosmic rays, we keep asking whether anything in our universe, now or in some distant future, might ever come close enough to that upper limit for its hidden rules to show themselves a little more clearly. When people imagine pushing toward the ultimate heat, it is natural to picture building some immense machine, a kind of cosmic furnace that squeezes matter and energy together until the thermometer hits the top. But the more you think about it, the more the universe seems to have built-in safety rails. If you compress too much energy into too small a region, gravity does not simply stand by and watch. It wraps that region in an event horizon and turns it into a black hole, shutting the experiment down almost as soon as it begins. At truly extreme densities, this is not just an engineering problem. it is a physical veto. Even if you somehow manage to heat a patch of space all the way to the Planck temperature, that patch might not remain a recognizable region for long. Space-time itself would be shaken so violently that the idea of a fixed location, a stable container with walls and a well-defined volume, could lose its meaning. The very act of trying to hold a system at that limit might erase the system you started with. And yet, nature has already ventured there. The early universe is the clearest example, when everything we now see was compressed into a state so hot and dense that our usual language falters. Some speculative cosmological models go further. In versions of eternal inflation, new bubble or pocket universes may constantly be budding off from a larger inflating space, each beginning with its own brief Planck-era blaze. In certain higher dimensional scenarios, collisions between extended objects called branes could also trigger temperatures near the Planck scale in their aftermath. These ideas are tentative, but they hint that absolute hot, while unreachable in any lab, might not be a one-time event in the wider multiverse. Black holes bring their own layer of intrigue to the story. We often picture them as perfectly dark and cold, swallowing everything and giving nothing back. That picture changed when Stephen Hawking showed that quantum effects near the event horizon make black holes glow very faintly. This Hawking radiation gives each black hole an effective temperature. Curiously, the heavier the black hole, the colder it is. A supermassive black hole weighing as much as millions of suns would have a temperature only a tiny fraction of a degree above absolute zero. The hottest black holes, in this sense, would be the tiniest ones. Hypothetical small black holes, perhaps created in the early universe, could reach temperatures in the billions or trillions of degrees Fahrenheit as they evaporate in their final moments, releasing a brief, intense burst of radiation. Even so, these temperatures are still far below the Planck scale. To come closer, we have to look not at the horizon, but at what our equations say lies deeper inside. Classical general relativity tells us that the mass of a black hole collapses to a singularity, a point of zero volume and infinite density. At that point, space-time curvature becomes infinite, and our formulas simply break. If this picture were literally correct, the conditions there would exceed any attempt to define temperature. Most physicists, though, suspect this singularity is not a real physical object, but a sign that classical relativity is being pushed beyond its domain. In a full quantum theory of gravity, the interior might be replaced by a region with finite but extreme density and curvature, perhaps associated with Planck scale energy and temperature. If so, a black hole could hide something like absolute hot permanently behind its horizon, a tiny region where space-time is as compressed and energized as it can be. From the outside, we would never see it directly. We would only see the shadow, the radiation, and the way the black hole bends light and matter around it. The idea of a horizon itself is central here. A horizon is not a physical surface. It is a boundary in space-time beyond which events cannot affect a given observer. The event horizon of a black hole is the most famous example, but there are others. In an accelerating universe like ours, there is a cosmological horizon beyond which light emitted today will never reach us, no matter how long we wait. Near such horizons, quantum fields in curved space-time behave in ways that look strangely like thermal physics. Temperatures emerge from geometry. Hawking radiation is one expression of this connection. Another is the Unruh effect, a prediction that an observer accelerating through what another observer calls empty vacuum will perceive a warm bath of particles. The faster the acceleration, the hotter this perceived glow. Push the acceleration high enough into regimes where curvature and quantum effects are intense, and the associated temperature climbs toward the same scales that appear in discussions of absolute hot. Heat, in these examples, is not being generated by a stove or a star, but by the interplay of motion, horizons, and quantum uncertainty. Some more speculative ideas imagine white holes, the time-reversed cousins of black holes, regions from which matter and energy emerge, but into which nothing can fall. They appear as mathematical solutions to Einstein's equations, though we do not know if they exist in nature. In certain models, black holes and white holes might even be connected in a wormhole-like structure, with matter that falls into one emerging from the other. These pictures are highly uncertain, but they are attractive because they suggest a way that Planck scale conditions hidden behind horizons might be linked, however indirectly, to the broader universe. All of this points to a deeper thought. If space-time has a smallest, meaningful scale, as many proposals in quantum gravity suggest, then there may also be maximum values for quantities tied to curvature and acceleration, and thus for the temperatures associated with horizons. In that view, absolute hot is not just a property of matter, it is a property of geometry. It marks the point beyond which even the notion of a horizon with a well-defined temperature stops being meaningful in the way we currently define it. You can picture a more restless version of this story as well. Instead of smooth horizons around large black holes, imagine the tiny, rapidly changing horizons of microscopic black holes bubbling in and out of existence in space-time foam. Each would have its own temperature, its own brief thermodynamic character. In such a frothing medium, the Planck temperature might not be a rare spike, but a constant presence at the smallest scales, stitched into the way reality is built, while larger, calmer systems average out those extremes. Black holes, white holes if they exist, and the horizons connected with them are important here because they are the natural testing grounds for these ideas. They combine strong gravity, high energy densities, and quantum effects in ways that nothing else does. Even if they do not quite reach the Planck temperature in a conventional thermal sense, they sit closest to that frontier of any objects we can observe. In the effort to understand that frontier, string theory offers one of the most ambitious frameworks. It reimagines the basic building blocks of the universe not as structureless points, but as tiny one-dimensional strings. Each string can vibrate in many different ways, and each pattern of vibration shows up to us as a different particle, an electron for one mode, a photon for another, perhaps a graviton for yet another. This simple change from points to strings softens some of the infinities that erupt when we try to include gravity in ordinary quantum field theories. Strings also bring their own thermal story. One of the most intriguing features is something called the Hagedorn temperature. This temperature is not equal to the Planck temperature, but it plays a similar role within the stringy picture. If you heat an ordinary gas, adding energy mostly makes the particles move faster and the temperature rise without bound. In a gas of strings, adding energy does something more complicated. Strings have an enormous number of possible vibrational patterns. As you pump in more energy, the system spends more of that energy exciting new modes, rather than simply increasing the average speed of motion. The number of available vibrational states grows exponentially with energy. As you approach the Hagedorn temperature, adding more energy does not raise the temperature very much. It goes instead into creating longer strings, heavier states, and more complex vibrations. In a sense, the system soaks up energy by changing its internal structure rather than by getting hotter in the usual way. It is like heating a pot of water at its boiling point. The temperature holds steady, while the added energy goes into turning liquid into steam. For a time, physicists thought the Hagedorn temperature might be an absolute upper limit. Later work suggested it is better understood as a kind of phase transition. Above it, the system may move into a new regime, where descriptions in terms of individual strings give way to something more like a gas of small black holes or a different collective state entirely. In many versions of string theory, the Hagedorn temperature lies not far below the Planck scale, making it a possible stepping stone. It might mark the last place where temperature behaves in a way we still recognize before deeper structures take over. String theory also reveals surprising dualities, relationships where two very different-looking physical situations turn out to be mathematically equivalent. Some of these suggest that a very hot gas of strings can be described equally well as a collection of black holes, and vice versa. In that picture, extreme heat and extreme gravity are not just related. They are two ways of talking about the same underlying physics. Thermodynamics, quantum mechanics, and geometry become tightly entwined. All of this remains largely theoretical. We cannot probe the Hagedorn regime in a laboratory, and we have yet to confirm many of the extra ingredients that string theory predicts, like additional spatial dimensions or certain kinds of symmetry. The theory's richness is both its strength and its challenge, but the idea that a maximum temperature might signal not a hard wall, but a doorway into a different description of reality is compelling. It suggests that absolute hot, rather than being just a final number, could be the point where the very language of hot and cold starts to give way to something more fundamental. Temperature is one of the most familiar quantities we measure. We attach numbers to it with thermometers. We feel it on our skin. We see its effects in melting ice and boiling water. It is defined in our usual microscopic picture through statistics, averages over countless particles in motion. As we drift toward the Planck scale in our thoughts, following heat as far as it can go, we begin to see how that everyday definition might slowly come apart, and how the universe, at its most extreme, might not recognize temperature in quite the way we do. When we talk about temperature in the usual way, we imagine a crowd of particles you could, at least in principle, label and follow. Each one carries some kinetic energy. Temperature is the quiet summary of all that motion, the average energy per degree of freedom. It is not the property of a single particle, but of the whole chorus, sharing energy until things settle into equilibrium. All of that assumes that particles are a good way to describe what is there, and that their motions play out on a background of space and time that behaves itself. As you drift upward toward the very top of the scale, those assumptions start to shake. Matter is no longer a gentle collection of atoms, ions, or even quarks. The energy density becomes so high that gravity stops being a soft background pull and becomes a restless actor in the story. Space-time itself may flutter with quantum fluctuations, changing shape on scales smaller than anything we can currently probe. In that kind of environment, the idea of temperature as a calm average over many well-defined motions begins to lose its footing. It is like trying to measure the temperature of a liquid that is constantly boiling into vapor and condensing into something else so quickly that there is never a stable liquid to talk about. At the Planck scale, the medium might not be ordinary spacetime at all, but a quantum foam where energy, geometry, and even cause and effect are all flickering together in ways that refuse a fixed description. Both of our great theories quietly assume more stability than that. General relativity imagines space-time as a smooth continuum that can bend and curve but not break into discrete pieces. Quantum mechanics usually takes that space-time as a fixed backdrop against which probabilities play out. If the Planck regime dissolves both the smoothness and the fixed background, then temperature, defined inside those frameworks, may dissolve with them. It is not just difficult to measure. There may simply be no underlying quantity that matches what we normally mean by temperature. Time adds another subtle twist. To speak of a temperature, you need the notion of equilibrium over time, a period long enough for energy to be exchanged and averaged out. Near the Planck temperature, time itself may not behave like a simple, steadily flowing parameter. Some approaches to quantum gravity suggest that at the smallest scales, both space and time are granular, built from discrete events rather than a smooth stream. If time arrives in tiny, jittering steps, or if different histories branch and interfere, the calm, continuous conditions needed for ordinary thermodynamics may never form. From another angle, temperature can be seen as a statement about information. When you call something hot, you are quietly admitting that you do not know which detailed microscopic state it is in. The higher the temperature, the more possible microstates are compatible with the same macroscopic conditions, and the more information you are missing. Modern ideas like the holographic principle suggest that the total information capacity of a region is not set by its volume, but by the area of its boundary measured in Planck units. If that is true, then as you cram more energy into a small region and push its temperature up, you are also marching toward a maximum information density. Once you saturate that bound, there may simply be no more distinct microstates available. In that situation, increasing the temperature might not be a meaningful operation anymore. You would have filled the system's state space to the brim. Black hole physics makes this connection very sharp. The temperature associated with a black hole through Hawking radiation is inversely proportional to its mass. The smaller the black hole, the hotter it is. Its entropy, a measure of how many internal configurations it could, in principle, have, scales with the area of its horizon. A black hole with roughly the Planck mass would sit close to the point where the ideas of maximum information density and extreme curvature meet. Beyond that, the natural language may not be temperature at all, but geometry. Some theorists picture the Planck temperature not so much as the hottest possible state in a naive sense, but as the point where thermal energy and space-time curvature fuse into one description. At modest energies, you can talk about hot matter in a cool background. Near the Planck scale, that separation evaporates. The geometry is the medium that is excited. Asking for a temperature there might be like asking for the color of an equation, an understandable question from our perspective, but aimed at the wrong level of description. All of this reminds us that temperature, for all its familiarity, is an emergent idea. It works beautifully for gases, solids, plasmas, and even for black hole horizons, because those systems have enough structure and enough stability to support it. we should not automatically expect it to make sense in every conceivable state the universe can take. At the bottom of the scale, quantum mechanics quietly stops us from ever reaching perfect stillness at absolute zero. At the top, the entire framework that lets us define temperature in the first place may give way to something deeper. That something deeper would still have properties we could try to describe: energy density, curvature, perhaps topological features of space-time itself. But they might not map neatly onto our everyday thermal vocabulary, just as classical mechanics had to yield to quantum mechanics. When we looked closely enough, whatever lives beyond the Planck scale may require not just new equations, but new basic concepts for what exists and how it behaves. In that sense, the Planck temperature is not only a large number perched at the top of a chart, it is a conceptual boundary. It marks the point where a familiar, intuitive quantity stops being part of the language of physics as we currently speak it. Thinking about that boundary is both humbling and strangely uplifting. Humbling because it shows us exactly where our tools fail. Uplifting because it points to where the next tools are waiting to be invented. When you follow that boundary back through time, you arrive at the Planck epoch, that tiny slice of history about 10 to the power of minus 43 seconds after the beginning. Before that, we do not yet know how to talk about the universe at all. Just after it, we can say only that energy densities were extreme and that if temperature was a meaningful concept, it hovered near the Planck scale. The forces we now separate into gravity, electromagnetism, strong and weak, may have been blended into one. Particles, if they existed in a recognizable way, were likely massless and interchangeable. Space-time itself may have been wildly curved or not yet fully settled into the smooth fabric we model today. As the universe expanded, it cooled with astonishing speed. In far less than a heartbeat, it fell from that initial peak to temperatures where the strong force peeled away from the others, then further to where the electroweak force split into the electromagnetic and weak forces. Each step in that cooling changed the rules, granting particles mass, allowing atoms to form, and laying the groundwork for stars, galaxies, and eventually the quiet structures of daily life. The Planck temperature is the high crest from which that entire thermal history flows. If you turn your thoughts toward the distant future, the same number appears in the background in a different way. In a universe that keeps expanding and accelerating as ours seems to, the average temperature will continue to fall. Stars will exhaust their fuel, black holes will slowly evaporate, and over unimaginable stretches of time, the cosmos will drift toward a thin, cold state not so far above absolute zero. In that picture, the Planck temperature is a one-time event, a brief flare at the very beginning that will never recur. Other scenarios are more cyclical. In some models, the universe could one day reverse its expansion and begin to contract, heating up as everything falls back together. In the final moments of such a big crunch, energy densities could again soar toward the Planck scale, briefly revisiting conditions where our current physics falls silent. More speculative ideas imagine a chain of universes, each born from the collapse of a previous one, or perhaps sprouting from deep inside black holes. In those stories, Planck scale states are not just a single flash in our past, but recurring thresholds through which new worlds are born. Whether or not those possibilities turn out to be real, the role of absolute hot remains the same. It is a pivot in the narrative of any universe like ours. It marks the upper edge of what our present theories can say, just as absolute zero marks the lower edge. Between those extremes, the long cooling after that first instant has created a universe roomy enough and calm enough for structure, chemistry, and life. The atoms in your body carry the imprint of that cooling. The forces that hold them together were tuned in those first fractions of a second after the Planck era. The space you move through, the time you feel passing, and the gentle temperatures you experience every day all descend in a long, slow curve from a state that may not even recognize temperature as we use the word. There is a quiet kind of comfort in that. The hottest possible condition is not something that threatens to intrude on your world. It belongs to a time and perhaps to places that are immeasurably distant from here. Yet its existence helps set the stage for the cool, moderate universe you inhabit now. The same laws that brush against their limits at the Planck temperature are the ones that let stars shine steadily, let planets hold on to air, and let a room stay warm or gently chilled. When you think of absolute hot in that way, it stops being just a remote curiosity. It becomes a reminder of how wide the range of reality really is, from the wildest extremes down to the softness of an ordinary night. Somewhere, at the very top of that range, our current language breaks and new ideas will one day take its place. Down here, far from that edge, you can simply rest inside the long, cool aftermath of that initial fire, knowing that the same universe that once touched that unreachable heat now holds enough quiet for you to drift, slowly and safely, through your own small stretch of time.